Hello guys, welcome to this video editorial of a problem in Starter 17. So the problem name is yet another counting problem, and yeah, this is the video editorial for that. I'll start off with a basic introduction of myself. I am Istasis Mishra. I am a fourth year undergrad at IIIT Hyderabad. I have been to ICPC regionals twice in my first and second year, and I have represented India in IOI 2018. So now that's out of the way, we can jump right into the problem. So let's try to understand the problem statement at first, okay? So it says, so the first part is not really a part of the problem statement. So the second para says that you're given an array containing n distinct integers. So all the integers are distinct. You have to count the number of ways to form sets of disjoint increasing subsequence of A. So this is it. So this is the problem that you are supposed to solve. So the next lines just try to explain what these three lines mean. So there's no need to read that here. I'll just explain it my own way. So let's say you're given an A 1, 2, 3, 4. Okay, you need to find the number of ways to create disjoint increasing subsequence of A. Okay, so 1 will be 1, 2, 3, 4, right? So all of these are increasing subsequences. Each of the sequences, this is a sequence, this is a sequence, this is a sequence, this is a sequence. Each of the sequences are increasing, right? And also they are all disjoint, right? So for example, you can't do 1, 2 and then 2, 3, right? This is not a valid thing to count. Why? Because it's not disjoint. 2 appears in 2 of the subsequences, even though both the subsequences are increasing, right? So let's say you had 1 here. Okay, so if we had not 1, let's say it was something like 4, 3, right? 4 and then 3. So this will still count, but now this will not count. 1, 2 and 4, 3, right? This will not count. This will count. This will also not count. 3, 4. So why will this not count? This will not count because 4, 3 is not an increasing subsequence. Why will this not count? Because 3, 4 is not a subsequence at all, right? So it needs to be increasing, disjoint increasing subsequences of A, right? So you have to count the number of sets of disjoint increasing subsequence of A. So let's see what the problem statement is trying to explain. Formally count the number of sets S, S1, S2, S3 up to Sk such that each of the Si is an increasing subsequence of A, and if I is not equal to J, then Si and Sj are disjoint, right? So Si and Sj will not have any elements in common. Okay, so now that we understand the problem, we can go about seeing what the solution is. The solution is actually of the topic DP using bit masks, right? So hopefully you have used bit masks before. Bit masks are basically, so let's say the number 3. The number 3 will be 1, 1, right? In binary. So since there are 4 elements, let's make it 0, 0, 1, 1. Okay. Right. So 0, 0, 1, 1. So 3 actually represents this set 1, 2. Right. 5 will be 0, 1, 0, 1. Right. So 0, 1, 0, 1. So every element that is 1, that this set will represent. So 5 actually represents this set 1, 4. Sorry. Okay. So now that we know what bit masks are, I'll not be introducing DP, bitmask DP here. I'm assuming you guys already know what bitmask DP is, and then I'll be trying to explain the solution. Yeah, so these are the states that we will have. Okay, so let's say f is calculating our solution for the given states, and f will have two things, I and mask. Okay, f of I mask is actually calculating, so forget the mask. So this I, it says consider only the first I elements. Okay, what this mask does, we'll come to it later. Okay, so let's say our I is till here, right? The last element is not yet considered. So let's take one example set that we will have counted 1, 2, or rather 1 and 2 and 4. 1 will be one subsequence, and 2, 4 will be another subsequence. One more thing that you can do is 1, 4 is one subsequence and 2 is one subsequence, right? So this whole thing may not be a subsequence, but each of them must be a subsequence. So these are two possible sets. Okay, and now we come to 3. Here, where all can 3 be added? 3 can be added here, but not here. Okay, 3 can be added here, but not here, right? Is that right? So we don't need to actually consider, so in this first set, we don't need to consider this 2 at all. This 2 is not needed, right? To compare. So why do we need to store 2 at all? We don't, right? So we just need to compare 3 to 4 and see if 3 can be added there. If yes, good. If not, then too bad, we'll not count it. 3 can it be added after 1? It can be. So we only need to look at the last element of each of the subsequences. So let's represent this subsequence as a set of 1 and 4, and this subsequence as a set 2 and 4, the last elements. And also the problem states that these two are equal, so the order does not matter. So these two are represented by the same set, 2, 4, right? So it does not matter if 2 comes first or 4 comes first, right? I'm just writing them in the order that they appear in the array. Okay, so 1, 4, what will be the mask of 1, 4? We just saw it's 5, right? And 2, 4, what will be the mask? It will be 6, right? So what this fi of mask represents is, consider the first I elements and then look at mask. The set of elements in mask are the last elements in their subarrays. How many in their subsequences, and how many ways is it possible to achieve that? So how many ways are there so that the last elements of the subsequences are represented by mask considering first I elements, right? Now what is the base case? Base case can be, look at the first element, so f of 0, and what are the possible values of mask? Either 0 or 1. So we have two base cases. Okay, for the first element we are already calculating it. How many ways are there to make 0, 0? So there are no elements in the subset. It's an empty set. Number of ways is 1, just one empty set, right? here 1 means you are considering the first element, right? The first element is in the, so you are considering this subset, yeah, this set. So how many ways are there to create this? 1, right? There's only 1 way, because there's only 1 element you are considering and you are taking it into account. So this is your base case, right? Now moving on to the most difficult part, which is the recursive case. So firstly, f of I mask. So if I is not in mask, so I is not in mask at all, what do you do then? The answer is actually just f of I minus 1 mask, because you cannot consider I anyway, right? So whatever the possible subsets you got in the previous index, you just, the number of ways will be the same, right? Now else there are more conditions, right? For, so yeah, no, else, I mean, otherwise there will be only 1. So there are a few possible cases that you need to add. So summation. So you need to find a number of ways, and hopefully you are acquainted with combinatorics, the rule of sums, right? So first we consider, so now we have 2 options. We can either put I in one of the sub-arrays, one of the subsequences, or not at all. If we don't put it in any of the subsequences, the answer will still be f of I minus 1 mask, right? Plus yeah, the I minus 1 mask we need to XOR with the ith bit. Now we need to add more things. So summation of all the j's less than I mean j, let's just write it in the j equal to 0, j less than I, and also one more condition is there. Let me write it properly. Yeah, summation of j equal to 0. One condition is j must be less than equal to less than I, and also aj must be less than ai, right? So if aj, so I'm assuming that j is not a part of that mask. Okay. Yeah, j is a part of that mask. So right now j is not a part of my mask. Okay, if j is a part of my mask, so let's say 0 1 1 0 1 1 0 1. So let's say my I is here, and if j is here, that means there is a subsequence ending in j, and I need to count the subsequences where I can add I. So if I add I and j is also a part of it, you can't count it, right? You can't add it to that subsequence. So you need to add it only if j is a 0. So if j is a 0, what that means is that I overshadows j. So let's say the value of j is 2 and the value of the ith index is 4, right? So you can, so aj is 2, 2 is less than I, right? So there are actually 3 conditions. I'll need to write it again. J equals 0. First is j is less than I. Second is aj less than ai, and j is 0 in mask. I mean, I can write it more formally. Mask of j is equal to 0, right? So only then you can add it. So in this case, it will be f of I minus 1. So mask, so let's say this is your j, this is your I. So what is the mask that will be coming from? So other everything will be same, right? But j will be a 1 before and I will have been a 0 before. So we are going from this state to this state, right? So if I was 0 and j was 1, that means there is a subsequence that ended at 2, right? And now I'm adding 4 to it. So that means this 2 will not be a part of my mask anymore. This 4 will be. Okay, so we are going from this to this. So how do we go from this this mask to this mask? So it will be mask of XOR 1 j XOR 1 I, right? So from here I'm setting j and unsetting I, right? So this is actually your solution and you're done, right? This is not very difficult to understand if you have already solved a few problems on bitmask DP. This is actually not that non-trivial as well if you think about it. Like, if you knew that you need to use bitmask DP here, this problem wouldn't have been so difficult, right? The complexity of this solution will be so how many states are there? This can have n different values. This can have 2 to the power n different values. For calculating each of these, you need to do O of n work, O of n per state. So overall complexity is O of n square 2 to the power n. So theoretically, this shouldn't pass the test cases, but there are a lot of constant factors involved. For example, all these if statements are there. So it's kind of like divided by 4, 5, 6, like the constant factor comes into play here. So it does pass. Okay. So I'll briefly explain the code now, the implementation of this problem, this exact same solution that I just explained. This is actually the tester's solution. It's written in C++, so hopefully you understand. So it just calls the solve function, right? So from main, it just calls the solve function for each test case. So yeah, this part is just input. This is the DP. Here you are setting the base cases, right? Now, yeah, now I starts from 1, goes till n. Now for each of the mask till the ith mask, if the ith mask is 0, if I is not a part of the mask, then it's just mask I will be equal to mask I minus 1, right? Else you start with mask this value, right? This is when you are not including I in any of the subsequences that mask already represents, right? And now here for each of the j's that are less than I, if v of j is less than v of I and j is unset, j is 0, the jth bit of that mask is 0, then you add this value that I just explained, right? So this is setting j and unsetting I minus 1, and then you take the mod. In the end, you need to sum among all the masks of n minus 1. So yeah, this is something that I missed. Is in the end your solution will be, this is your answer. Answer will be equal to summation of mask goes from 0 to 2 to the power n f of n minus 1 mask. So this is your answer. Why is that? Because you consider all the n elements, and for each mask represents a different subsequence, right? A different ending value, set of ending values of subsequences, right? So you need to add all of them. So in the end, if you add all, take the mod, you just print it, and that is it. This is not very difficult to code up as well, right? So this is the tester solution. I just explained the tester solution. You can find it in the written editorial as well. I hope you liked solving this problem, and you'll be seeing me in the future editorials as well now. So yeah, have fun solving problems, and we'll be meeting later again. So thanks for joining. Goodbye.